Hi. Just a small correction about my affiliation. I'm not working for ResearchGate anymore, but this doesn't change anything. So we're still going to have a great time. I'm very excited to stay in front of you because I think you are a great audience to tell a great story. And in this story, I have incorporated systems from algorithms. I have incorporated elements from systems, algorithms, a little bit of philosophy, and even a joke. And this is because these are multiple projections of the world, and the talk is about random projections. The talk is also connected to big data. And I think big data requires big questions and big thinking. So I have a big question for you. So listen well. So which do you think is harder? Is it search or is it machine learning? So we'll revisit this question at the end. And maybe you'll see another perspective in which you can answer this question. We'll start with search, and we start with text search, because text search is the most popular kind of search. And why does text search work? Well, it's not only because of the systems that have implemented text search engine, but because of the properties of the data. And if you think of textual data, so this data has two important properties so text search can work. First, the data is very, very sparse, 99.9%. So this means if you pick some document, this document is going to have 0.1% of the words that are in the language. And then the second reason that it works is that when we query with words, which are very strong query features. Okay, so this is a special data, that's why it works. But if you switch the domain, say images, okay, images have different properties. So first, data is not so sparse. So for example, here's the image of the digit 3, so it has 20% of all the possible pixels that carry information. But if you try to search similar images to this image, now you cannot just take 3 pixels. Now, in text search, you can take 3 words, but in images, you can't take 3 pixels. So these are properties that are fundamentally different, and it's basically different kind of data. Okay, so to position the talk, I choose to think of 2 kinds of search. One search is for sparse data, where the query tends to be short, and this is keyword search solved with the inverted index. Now, if your data is dense and your query is long, for example, the image, it's going to be a long query with lots of pixels. Now, this requires a different search method. And the random projection method, it turns out that it can work for dense data, not so good for sparse. But there are some use cases for the dense data, including image search, semantic search, and recommendation systems. So my plan is to walk you first through some basic concepts about representation of data. And this is material we're going to just go through to put everybody on the same page, and because it should be familiar. But then we revisit this algorithm of random projections. And third, we actually demonstrate how it works on real data. So let's get started. So we have an image, and image to the computer is just pixels. And if you are a data guy, you take the pixels and you create a vector. Okay? So if this image has 800 pixels, now here would be 800 dimensions. So it would be a long vector. If you work with a data set with lots of images, you take each image, make it a vector, and then stack the vectors on top of each other, make a matrix. So this is pretty much common currency in the data world, so people work with matrices. So same story for documents. You can represent them as vectors. The dimensions are the words. But there's a fundamental difference, so this data is sparse. Okay? And the image data was dense. If you get another kind of data, click data from your website, it's again can be represented as vector. So this vector is going to represent the user who clicked, and the user clicked on the first book, so we're going to write 1 in this vector. Okay, so 2 kinds of data going to the beginning, and dense data represented with dense matrix, and sparse data represented with sparse matrix. So one you can search with Lucene, the other you cannot search. Now, people, especially in recommendation systems, like to take this sparse matrix and make it dense. Okay, so once you make it dense, you cannot search it anymore. Okay, so why do people choose to make the sparse matrix dense? By the way, this has a name called dimensionality reduction. And here is a very simple method to accomplish dimensionality reduction. Simply find words like beer and wine that are correlated or somehow semantically similar, and they are represented by these 2 columns, and then merge the columns together. Now, if you merge a lot of columns together, you're going to end up with matrix that is with fewer columns, but the information density is higher. So you have condensed your matrix. Okay? So why do you want to do this? Well, if this example is not convincing, let's look what happens to images. So you have if you take images and you run some dimensionality reduction algorithm, then this dimensionality reduction discovers patterns. For example, for 3, it discovers that 3 can be created by superimposing these 2 patterns. And by the way, these are not the only patterns that are needed to represent the 3, but these are one of the most dominant. So when people say dimensionality reduction, they actually want to do pattern discovery. And when they do this dimensionality reduction, the data gets dense. Now, we're reaching the method that I will talk about. So it has a fancy name, random projections. And projection, this is a geometrical notion. But if you look at the field of machine learning, so projection, this is basically a dot product. If you take linear regression, so linear regression is a projection. Okay, if you take a tree, it also uses multiple projections. So a lot of stuff in machine learning is about dot products and about projections, and here it's doing this stuff randomly. Okay, so it's really surprising that it works if you come to think this way. But also what is interesting here is that this is a very foundational topic that connects a bunch of learning algorithms, like random forest. So are people familiar with random forest? Okay, support vector machine? Okay, can you connect the random forest to the support vector machine? These are quite different. Okay, but there are some recent advances that when they represent the support vector machines through random projections, and you can see some connections. This is very interesting. And on the other hand, SVD, one of the most scalable algorithms for dimensionality reduction, they rely on these techniques to make it scalable. And finally, which is the main topic for today, is the nearest neighbor. Okay, nearest neighbor, machine learning algorithm, but it's also a search. So this is a machine learning which you do through search. So there are connection between these 2 different fields. Now in practice, previous slide I talked about the theoretical foundations and theoretical interests about this method, but in practice some companies have incorporated this method into their systems. For example, Spotify, they developed a tool which is available online and which I will demonstrate. They use this method for music recommendations. Okay? Another company, Etsy, also uses this as part of their pipeline. You should also know this random projection method sometimes is referred as locality sensitive hashing. Okay? So this is another view. There are multiple views of this projection. One is geometrical, another is hashing, and this makes it very exciting. Now we've reached the second stop for today. So how does this thing work? We just know it's random, and it's a projection, and let's see how it works. At a high level, I said you want to search through this matrix. So if the first row could be some user, Okay, it's the vector. It's a vector which is representing a user of your website, and every row it's a different user. So if you want to find more similar users, you can basically do brute force. Yes, just go scan through the matrix, compare every row to the query. But what you can think here, you could, and what I'm going to show here, you could do it a bit smarter, more efficiently, if you take the information from this matrix and represent it as trees. And trees are searchable. Okay, let's see how it works. If you have a data set that has only 2 attributes, now we are living in 2 dimensions, and 2 dimensions you can visualize. And the first row is red, it's a data point, so I'm going to represent it here. Okay, it's this red dot. Now the green row is a data point here. Okay, so every row is a data point. Now the search in this framework is also known as the nearest neighbor problem, and you start with a query, you want to find the closest point to your query. So in 2 dimensions you can visualize it, but in high dimensions it's very difficult. And so here's the first tip. Okay, instead of doing brute force on the whole data set, we can restrict the region around the query and do brute force only in the region. So there will be 2 stages. One stage is candidate selection, just select, somehow find this point in the circle, and then with brute force evaluate every point. Okay, but finding this neighborhood is very hard. So now we do another approximation. And the core idea is to partition our space into random grids. So these grids will be dynamic. Okay, so we put more lines, more partitioning where there are more points. And we do it randomly. So there are a bunch of reasons why you want to do it like this. We can talk later, but one reason is that random is actually cheap. Okay, and later we'll see there's also another reason why you want to do it randomly. Okay, so let's start. I put a random hyperplane and I split the data set into 2. Okay. Now going back to this foundational concept of the projection. So what is the projection? Well, the projection is basically shining a light perpendicular to this, shining a light parallel to the splitting line. And here, it's like you have a random direction and you put your data set on this random line. And this means a histogram. Now, in 1 dimension, you can look at the data. Okay, so basically, this is the method. It's nothing fancy. Linear regression does like this, works in exactly the same way. You can think, okay, linear regression with lots of attributes, but in the end, it's going to project the data, and it's going to put the whole data into 1 dimension. Okay, and this reminds me of Plato's allegory of the cave, and here's the philosophy component that I put in the top. So Plato wrote this story about the prisoners who live in a cave. So they're chained in the cave, but there's a whole world outside the cave which they can only see the shadow of the world. They can only see the projection of the outside world on the cave wall. So the outside world could be 3 dimensions, but they can see only 2 dimensions. So the philosopher's goal is to escape from the cave and to understand the outside world, but they can only see in 2 dimensions. And now it's similar for the data scientist, okay? So the data scientist can see only this thing, okay? But the good data scientists, they want to escape from the cave, which, by the way, is known as the curse of dimensionality in machine learning. So they want to escape from the cave and bring the light. Let's continue with the algorithm. Partitioning into 2, this can be represented as a tree. So the red points are in the red branch of the tree, the green points in the green branch of the tree. Now, you basically take this idea and do it recursively. Okay, now you split. Again, we end up with 4 partitions. Let's run this method as simple as it is for a few iterations to get a feel what happens. So this is the second iteration. We have 4 partitions, then third iterations, 8 partitions, now 16 partitions. It's already very fine-grained, so we are going to stop. And what's the purpose of this? Well, the purpose was we started with this because we wanted to find the nearest neighbors. Okay? So nearest neighbors means close points. When 2 points are close, they're going to end up in the same partition, even if you do it randomly. And I'm going to emphasize this concept. Okay, they are likely, okay? They are not certain, okay? So when something is likely, to make it certain, what you do is you repeat it multiple times. And now from likely, if you repeat it enough times, it becomes certain. And you could think of each partitioning as exploring the space of the possible neighbors. So here's the red point, and we built one tree, and this tree explored the lower left corner of the space, okay? But you see there are points that are close to the query in the yellow part, okay? So what about these points? We're missing on them, okay? Then what you do is you run the second tree, and it explores a bit of some points in the upper part of the space. A third tree explores a different part of the space. So basically, build more trees. That's the conclusion. And if you run it and visualize it, what happens, how this exploration goes, okay, the more trees you add, the more you explore around. But if you add a lot of trees, you're now certain to have explored the nearest neighbor. You have seen them, okay, but you have seen too much stuff, okay? So now you are spending too much computation on this, okay? So next, we do a constraint. So we will constrain the region in such a way that it gets more. So we can basically ask, okay, we see neighbors, so you run your query through the trees, and every tree comes with candidates. Okay, so if some candidates appear in more trees, they're basically more likely. So this is this threshold in how many trees does the nearest neighbor candidate appear. And if you put a high threshold, now from this region, which is without any threshold, is going to shrink. So now your region of nearest neighbors, of candidate neighbors shrinks, and you're going to actually, because you have to evaluate them fully with brute force, so you want this region to shrink. And this idea it kind of reminds me of this joke about the 3 statisticians. So I'm going to tell you the joke because I want you to remember this method used in this algorithm, but also this method is in many other algorithms. So there are these 3 statisticians, they go hunting for moose. The first statistician shoots, and he misses 1 meter to the left. The second statistician shoots, he misses 1 meter to the right. And the third one, well, you think he would shoot, but he just says, good job, guys, we've got him, because he's averaging. So key point is when you go hunting for data, bring some statisticians, and you've got him. Okay, now we have reached our third stop, which is to see how the method that I described, how this method actually performs. Okay, I choose a data set that some people can be familiar with. This is from the website Kaggle, and this data set people used to teach themselves machine learning. In the past, people use this data set to develop neural networks and other learning methods. And this data set, so what I'm going to do is I'm going to use an image search as a prediction system. So I'll put an image, okay? This looks like a 3, could be a 3, could be a 5, I don't know. So I want to find the label of this image. And one way to do it is basically put it in a search system and see what comes. What comes has labels from our training set, and then we say, okay, the first candidate is a 5, so I'm gonna say this is a 5. So machine learning actually works with 2 data sets, the test data set and the training data, the training data set and the test data set. Now, because we're doing machine learning with a search, the so-called nearest neighbor, we have to do some indexing. So indexing means take the data and put it into an index. So roughly, it looks something like this Python code. So the key idea is that every image, it has a vector, okay, which we'll use for indexing, and it has a label, which we remember because we're going to need the label later. Now, for stage 2, I already described, but you put an image, you search, and you get the label of the top result. Okay, and this is Python code that looks like this. By the way, this is very similar to the Spotify tool, which uses Python. So this code is very close to what you can run. Now, I use the Spotify tool mainly, but I also developed a tool on my own because I want to get deep, and make sure that I understand everything. Because when I come here and present, you're going to ask me tough questions. I have to understand everything. So I developed a tool on my own. Okay, so I'm going to see these two tools. And this is also open sourced. So run the Spotify tool. Okay, so the Spotify tool, in the Spotify tool, I built 10 trees, okay, and each tree explores 1,000 candidates. So this is 1,000 candidates that need to be evaluated fully. It has a decent accuracy, 97%, but it's very slow. Okay, 5 milliseconds per query. Okay, you can do better. So how do you do better? Well, you take this dimension and you bring it down using this dimensionality reduction technique. And this is another bonus for this dimensionality reduction technique, that it makes cheaper the data smaller, and so it's cheaper to compute with this data. And once you did this, okay, the search time went down 0.7 milliseconds per query, but also the accuracy went up. And why is that? Because dimensionality reduction, as I said in the beginning, it discovers patterns. So the first line, it worked at the pixel level, while the second line, you could think, it worked at the concept level. So this concept level here is some patches from the image. OK, now there's another bottleneck. We basically evaluate fully too many candidates. OK, and here I put my tool, and I got the time roughly half of what I had before, but I had to build more trees. Now, to be fair, so it could be that I didn't really do a lot of tweaking on the Spotify tool. It could be that you could tweak it and reduce these candidates, and this tool could really even get lower. So this is quite possible. But the main point actually here is not about whether one tool is better or not. So it's more about some algorithmic heuristics. And there is some difference in the algorithms of these two, but kind of small difference. And the main point I want to carry across is that, OK, if you tweak a system like this, you are likely to get good performance, and in many cases, you're likely to get good accuracy. OK, now we've reached the question I asked from the beginning. So which is harder? Is it search or machine learning? And here in this talk, I presented a system that searches dense data, dense vectors, using these trees. And this indexing structure, it looks the following. You have the tree, and at the bottom, you have the point IDs. Okay? So when you search, you're walking these trees, and you find some candidate points, and you are evaluating them. Okay? And if you do machine learning, you could use the same thing. However, you could be, you don't have to store the full data. Okay? You could just, what is important for machine learning is predicting the label. So this label can come from many neighbors, and we can aggregate. So this is a key point here, that in the leaves we could store a histogram. So in this way of thinking, you could think, okay, this is search, okay. Search has to store more data. And when it searches, it has to be precise. And it really cannot borrow what's called statistical strength from many other points. But if you do machine learning, okay, you can aggregate your data, so this is cheaper. And because you borrow knowledge from many data points aggregating this histogram, it's actually, it looks like machine learning is easier than search. So this is my takeaway point. And in conclusion, I would say that this method is useful when you search for dense data, and the other application is that other algorithms are using it to become faster. And this is the end. Thank you very much.